Okay, let's get started. Good morning, good afternoon, and good evening, everyone. My name is Yijun.Fan. I'm the Product Marketing Manager for Adams and Easy5 at MSC Software. Here's a brief agenda for today's webinar. So we're going to talk about what is industrial robot, and just a brief intro on some of the engineering challenges and how Adams can integrate with some of the commonly applied control systems or control software. After, we're going to go through a pretty straightforward kind of workflow for you to just get some idea about how to start from ground zero. And following that, we will have our demonstration, in which we will actually do a live demo today, which I will open up Adams and MATLAB and show you some tricks. All right, first, robotics. We have a lot of, almost in every house, we have a Roomba to help us cleaning. So that's like a house appliance kind of robot, all the way to the Mars rover, the Curiosity. In between, we have things like the robots we use in the manufacturing plants. We have the rescue robot, or the robot we might use in like the military area. So today we're going to talk about a specific robot, which is the industrial robot. Industrial robot is defined basically as the robot that's helping with some of the either manufacturing process or other material handling process, like the ones you see in the big automotive manufacturing facilities, the one that we use to do the welding, painting, packaging, or simply picking and placing products. The robot we're going to talk about today is a typical 6 degrees of freedom, or we call it 6-axis industrial robot, like you see on the picture. Some of the engineering challenges, everyone wants to increase the efficiency of the robot. So with the same task, the shorter amount of time it needs to complete a task, the more efficient the robot is, which translates into cost saving, as well as increasing productivity. But there are problems that can be generated while you're trying to increase speed. For example, if you are applying a bigger motor, or if you're applying a larger acceleration to certain components, sometimes you will try to lightweight your robot to make it faster with the same amount of power source. With that, you can sometimes have some problems like generating excessive vibration, or sometimes there will be some deformation, or even things like the gear rattle effects. So all those will affect the precision and accuracy for your robot, especially when you are using that for a certain, like a manufacturing process. This is going to be critical, that you want to make sure while you're increasing the speed, you still maintain the accuracy of your system. There are two big pieces of a robot, we say, the hardware and the software. And we say the software is just as important as the hardware, if not more important. We know a lot of companies, they can manufacture the hardware very successfully, but they are still purchasing the software system from some of the bigger robotic companies like FANUC or like Siemens. So we say that control algorithm is one of the key factors for people to place themselves among their competitors in this industry, in this robot industry. So one of the things that you want to do is to validate your control algorithms. You want to make sure it works. People often use like control softwares like MATLAB Simulink to design their control systems. So those 1D systems are a very good tool for you to basically structure how you want to control your different movements or mechanisms. But there are also some limitations to that. For example, if you want to study how the manufacturer is contacting the workpiece and how that contact force is going to affect the accuracy, or if you want to take into effect the friction at each joint, or if you want to consider the deformation of certain components, those will be very hard to capture in the 1D system. And that's why we are saying that it is important to validate the control algorithm. There are two ways to do that. You can, of course, do that in a physical test. Another way we want to introduce today is to validate that in the virtual prototype, such as multi-body dynamics. I believe a lot of you have seen this video or commercial before. We call it commercial because it might not be realistic to achieve this kind of goal at this moment. And we know Tim Boyle, he's a very accomplished table tennis player, and KUKA robot is one of the major robot manufacturing OEM in the world today. But so far, as we know, what you see on this video is probably a little bit hard to realize with the current technology. Nevertheless, what it shows us is that what a robot can do with a very precise control system. So there are mainly two types of control algorithms that we say you can define to a robot. You can either do a predefined trajectory, or you can do a kind of feedback control system. With the feedback control, you can actually manipulate the robot based on the changing. So some of the reasons you need to validate the control algorithm is that first you need to calculate the compensation of load depending on the structure deformation. You also need to verify that through various different tasks. You would need something representing the real physics to basically as a platform for you to validate your control algorithm. For example, in this example, you can see we have almost a gear reduction system at each joint. In one of the gear pairs, we actually did a comparison with the gear with and without the backlash. So you see here with the blue curve is the displacement of the end effector or the object in case where there is no backlash between the gear pair. And the red curve represents the displacement in the situation where we actually introduce certain level of backlash. And you can see with those two different scenarios, the trajectory is different. And those vibrations, although it's pretty minimal if you are looking at the overall value, but sometimes those vibrations can generate a lot of problems for your system. Flexibility sometimes should be taken into consideration. And those are the things that are very hard to capture if you're only using the 1D kind of simulation. And that's the reason lots of the robot manufacturers like Fanuc and Denso, they're using the kind of Adams and control software Cosimulation to help them validate or to help them capture whether or not their control system works in their specific scenario. So how do we integrate with other control softwares, and what are the control softwares that can be coupled with Adams? So we have a tool called Adams Controls. Basically, it allows you to connect with control systems like EZ5, MATLAB Simulink, or any software that supports the FMI standard. FMI is a functional markup interface. It's a common kind of connection standard supported by lots of software. I think it's more than 30 softwares right now that supports the FMI standard. So through that portal, if, for example, Simulation X, MapleSim, those softwares if they support FMI, we can co-simulate, or we can couple Adams with that specific software. A quick case study. So this example is from ABB. What they're doing in this project is that they're not trying to design or redesign the hardware. What they're trying to do is to customize their control system so their robot hardware can be specified for different tasks. So in this case, they wanted to validate their controller development before the physical trials to shorten their R&D cycle, especially if they have multiple tasks or various different scenarios for the robot to be customized. Next, workflow. So if I am a beginning user of Adams, what are the basic steps you need to complete or create an Adams model and have it coupled with another control software? These are the steps that we took when we generated the demonstration model for today's webinar. So we started with the CAD, we started with the CAD. I mean, you can generate geometries in Adams, but if you want a pretty detailed or sophisticated geometry, we recommend that you create that from a CAD software like SolidWorks. After you have the CAD geometry, you'll basically export that and import the CAD geometry into Adams. When you have it in the Adams environment, you need to add things like the constraints, add like the mass properties, and the boundary conditions like motions or the forces. And at this point, you can start to perform some of the transient dynamic analysis if everything is defined correctly. Next, if you want to incorporate some of the flexibility, you can choose either to import the model neutral file from another finite element analysis. So we support that connection for most of the mainstream FEA software, like Nastran, Ansys, Abacus. Those software will be able to generate a file called a model neutral file. With that model neutral file, you will import that into Adams and make certain parts flexible. In this way, you will capture the deformation and even the stress and strain recovery of that component after you are done with an Adams simulation. As you see, you can directly read the volume stress information from the Adams post-processor when you are done with one simulation. So we do support stress and strain recovery. Next, when you have the flexible body in your system, you can also perform some of the vibration analysis. So you can calculate the natural frequency at different mode shapes. And when you have those vibration natural frequency, you can perform some vibration study to make sure that the operating frequency avoids all those potential natural frequency to eliminate the potential kind of resonance effect in your system. So in today's example, we are going to introduce a mechanism called the cosimulation, which means Adams solver will calculate the Adams model, and MATLAB Simulink solver will do the calculation for the Simulink. So in this scheme, each solver is doing its own specialty. So we're not trying to use one solver to calculate both models. We're asking each solver to be responsible for their each model. So in this way, you will get a pretty precise prediction for your entire system coupling. Of course, Simulink is one of the options you can choose. Yijun.Fan is a 1D solution of MSA software. It can support controls, and it's doing especially well in the hydraulics area. So if you are coupling a hydraulic system into your MBD model, we highly recommend that you can give a try to Yijun.Fan. And with that said, we understand that a lot of people are in MATLAB Simulink user, and that's why we chose that as the control platform that we're doing the demo with. All right, okay, that's it for the presentation. Now let's take a look at the demo. All right. Now let's open up Adams. What I have here is the latest Adams View 2016. This is my working directory. So currently what we have is the Adams model basically, and the end position is the kind of trajectory that we want the end effector of the robot to go through. And in this case, we have constructed an MSC as the sort of the letter that we want the robot to go through or to write. So that's it. Those are some of the files that you see in the current working directory. We want you to pay attention to that because later we're going to generate a few things that's going to be added to this working directory. All right. First, let's take a look at the Adams model. So here we go. It's not a very complicated model. It's a pretty typical 6DOF model. We have one flexible body. The vertical arm is flexible. We define, there are 6 degrees of freedom basically, and we use either motion or torque to define the boundary condition to define how those joints move. So what we can do here first is we can apply a constant value to that, and let's perform a very simple dynamic analysis just to make sure that everything works with the Adams model. As we can see, this ran successfully. Now, it's nothing fancy, just a very basic dynamic model to make sure that the Adams model works. Because if the Adams model doesn't work, there's no way you're going to make this cosimulation work. So this is kind of a prerequisite. So if you are to create this connection between the cosimulation, the MATLAB and Adams, and you want to use, for example, the MATLAB code to define how you want to move this robot, you will basically need to change your motion, the value of your motion and your torque into the input from MATLAB. So here you need to define a series of state variables. And all the state variables can be seen here. So all the inputs and outputs, each parameter needs to be assigned with a state variable. And that state variable goes into the boundary conditions that defines the movement of each joint. So in here, for this torque, we will replace the constant value with a state variable here. All right, with that defined, let's go to the Adams controls. First, to activate Adams controls, you need to go to Tools, Plugin Manager, and load the Adams control plugin. Then there is a tab called the plugins, and you will see currently there are 4 plugins to this system. One of the 4 plugins is Adams control. So you click that and choose Plan Export. Now what you are doing is to try to create the connection between your Adams model and your Simulink model. In this example, we are choosing the input signal. The input signals are the signals that Adams reads from your MATLAB model when you are doing the cosimulation. So in this example, for 6 degrees of freedom, we're using one torque. For one of the joints, we're using the torque. For other joints, we're using angular displacement or angular velocity. So from angle 2 to angle 6, we are using angular velocity or angular displacement. For joint 1, we are using the torque. For the output signal, we are giving MATLAB the end position of this end effector, the position of this end effector. So we are also giving MATLAB the speed or the velocity of joint 1, the angular velocity of joint 1, because I'll explain that later when you see the MATLAB model, is that we actually created a PID control for the joint 1, for the torque on the joint 1. So we need the feedback of the velocity, the angular velocity on joint 1. In target software, you can choose EV5 MATLAB, or if you're using, for example, Simulation X, you can choose the FMU standard. Here we will just choose MATLAB, and we leave the others as default. Here is the working directory. So now these are the model we have. And when you click OK, you will see that we generated a list of other files. So what it does is that it created a M file which imports the Adams model into MATLAB. So MATLAB can read that and incorporate the Adams model into its control algorithm. All right, let's open up MATLAB at this point. So I've set up the MATLAB working directory to the same working directory as I have with the Adams. Let's first take a look at the Simulink model that we have constructed for this particular demonstration. Okay, as you can see here, nothing too complicated. It's a simple demonstration. The basic idea, let's go from the left to the right. The basic idea is that you first need to define the end trajectory. So it's the XYZ position for your end effector that you want it to go through. What I did is that I created a trajectory in Adams, and I performed a simple dynamic analysis. And in the post-processor, I exported the motion. I exported the XYZ position as the Excel sheet table, which you can easily do. So that is the file that I directly got from Adams, the end position. In that file, you will see the trajectory of basically the XYZ position of your end effector that you want it to go through. So how do you translate that into the kind of angular velocity or the torque that you need to control each joint? There is a paper that shows you how to do that. It's called the inverse kinematics. I believe a lot of you have heard of that. There is a paper, I can point you to that illustrates how you can apply that for a 6 degrees of freedom robotics. So we used that inverse kinematics as kind of the formulation to generate the velocities, angular velocities you need to choose to realize or to accomplish your ideal kind of trajectory. So as you can see here, from joint 2 to joint 6, we're just taking a derivative of the angular displacement and got the angular velocity. So we're using the angular velocity to control the movement of the robot. But for joint 1, we're actually adding a feedback control system, and we constructed a PID control, so we're actually using the torque to control or to manipulate joint 1 instead of the velocities, because sometimes the torque is more commonly applied in real robot design. So it all depends on your requirements. So now what we are missing here is the piece where Adams model should be represented in the MATLAB Simulink structure. So the way we do that is to import the M file that we just generated using Adams control, and when you type in Adams, you will get the Adams block. This block represents the Adams model. So you will copy that and paste it into your Simulink environment. I'm not a Simulink expert. I'm just trying to make this demo work. I believe a lot of you are a lot more proficient in Simulink than I am. Okay, now you have the Adams model inside the kind of Simulink scheme. Now they are connected. And if you click into that, you can do some, you can do some modification. For example, I want to change the animation mode from batch to iterative. There's also a lot of things you need to modify. For example, this PID controller, this proportional, this P is very critical actually. I'm going to do, we have tuned this many times, So this is kind of the ideal number that we found for the specific PID control. So I'm going to try to perform a live run for this model, and then if it's successful, we'll try to change the PID, the proportional a little bit, and see what are the differences. So just to make things more interesting. So with that taken care of, you can start the co-simulation in Simulink environment. It will automatically open up the Adams model. We also have two plots, MATLAB plots. One is the ideal trajectory, one is the real-time trajectory. Okay. So here you can see the n effector is moving, almost moving through this MSC logo. And the real-time trajectory is almost identical to the ideal trajectory. It's just a little bit behind. And it's fairly precise. And later we will change the PID controller a little bit. And that's actually what you want, what you are doing in real life. It's you have to tune a lot of parameters, you have to tune a lot of settings to make sure that your control system works for your specific scenario. So now we can see all the lines are pretty straight, and the shapes are identical to each other. We're going to let it go through that, and we will change some of the PID. We will play with the PID control system a little bit, and you will see another kind of you will see that the real-time trajectory will not be as identical as the ideal trajectory after you did some modification to that. Okay, now you're done with the results with this Adams model. So this is the Adams model you used for the co-simulation. In the working directory, you will actually see a results file. So this is the Adams results file. It contains all the information of Adams through this co-simulation. And when you exported use Adams control to export the M file, it also exported a CMD file. So although it is identical to your original model, you know, if you didn't do any changes to that, but this is going to be the actual model that the co-simulation is using to conduct this simulation. So if you want, you can also open up that exact same model you used in this coupled analysis. Now let's import the results file. So in Adams, let's go to the post-processor. So that will play the same animation that you just saw the robot went through during the actual live run. And on the right-hand side, there are a number of results you can get. You know, the typical results you get from Adams simulation, like the force and torques, displacement, velocity, acceleration. You can all get those. There's one specific thing that I want you to take a look is the S-force. So this S-force, you remember that one of the joints we are actually using the torque to control the movement of that joint. So this is the actual torque that was generated according to the feedback control system and the PID controller. So if you Take a look. So this is the actual torque it needs applied to that joint to make sure that we have the correct trajectory as we want it per our design requirements. You can, of course, see other things like the tip displacement to check if this is what you need or this is different than your ideal trajectory. All right, to just make things more interesting, we are going to play around with the setting here a little bit. So let's change the proportion. Let's change the proportion a little bit. Let's try to run another analysis. Just want to show you that this is not always ideal. If you didn't define your control system correctly, you might not get what you wanted in the first place. Of course, there are other ways that you can provide your feedback control type of, you can provide your feedback control. You can, here we use the velocity at joint 1. You can also use, for example, the end displacement as a factor in the PID control or in your feedback control system. And here you see the shapes are a little bit different. With the real time, it's not as straight as what you wanted in the ideal trajectory. And if you see in the animation very carefully, you will also see that it is not going straight. It's actually going through a curvature around the corner. So in this case, you didn't define your control system correctly. You are not getting the ideal results you want for the original design requirements. And that's actually the fidelity you wanted to see with this kind of methodology. Here, as you can, I don't know if you can see that clearly, but those are not identical. There are some differences with the trajectory.